So the topic of my lecture is today the Global Positioning System Introduction, which is a part of the atmospheric and space science. To follow this lecture, this is a follow-up to my previous lecture given as a satellite navigation system as a part 1 lecture under atmospheric and space science. So within that lecture, we'll be covering the aspects of various GPS components, the error source of the GPS component, and how to tackle with that, and the use of GPS in different sectors in this modern era. So friends, let's begin. Myself, Debajyoti, a senior geoscientist. I'll be covering the important aspects for the Combined Geoscientist exam, the BARC exam, and the ISRO exam. Now, which are the important topics we'll be covering? First is the fundamentals of the GPS system, how the GPS works, the satellite receivers and the trilateration problems, the GPS error sources, which are very important aspect to look at, the satellite clock and the multipath error, and how we can utilize GPS in the scientific research and the exploration surveying and the mapping, the future of GPS and the limitation and its challenges. So now we'll talk about some introductory history and the development of GPS. GPS is the generally it's called global positioning system, which can refer to navigation system with the time and the ranging. It has been initially developed by USA, which is the satellite-based navigation system, which provides location and time data with the GPS receiver. It's in and 24 hours per day. Low-end user with cost military safe, having 10 to 20 meter accurate navigation position. Thereafter, it has been modernized in 2000s. It has undergone various launch of a new additional satellite and with the developments of additional receivers, which can improve accuracy and the coverage. Now, for the civilian use, it has been expanded in 1980, and it can lead to the rapid growth in the commercial application and the. Now, talking about the GPS component, there are control segment, there are user segment. Control segment includes master stations and the different monitoring station, and user segment is generally receives satellite signal. And there is also a space segment, which is the Napster, that is navigation, satellite, time, and ranging, having the constellation of 24 satellites. Now, US constellation presently can combine of 32 satellites, having a height of 20,000 around kilometer above the Earth. So there are 4 satellites in an orbital plane, 55-degree inclination to the equator with a 12 hours orbit. Now, the most important thing is how GPS works, how the satellite receivers and trilateration concepts come. So there are basically a network of satellite at the Earth. They can continuously transmit the radio signal. And there are GPS receivers on the ground. They generally pick up those signals and it analyzes the time it takes for the signal to reach from satellite to the multiple receivers at the ground. So as an example, we can show that there is a Napster satellite transmitter system which is transmitting the pseudo random code, that is one of the code, and there is a GPS signal which can receive this signal, radio signal, from the satellite and calculate and measures the time distance. So this time distance is multiplied with the speed of light. It can measure the distance of any point on the ground from the satellite. So in this way, generally, this is very crude idea or concept, rudimentary idea about how the GPS works. The advanced concept comes in. So what is a trilateration? So there are satellites. So each satellite is centered at the position of a sphere, the radius equal to the measuring distance. So to accurately measure distance, there should be more than 3 to 4 satellites. So generally receivers calculate the distance, which is the difference between the time of broadcast of the GPS signal and the reception of the GPS signal. It receives signal from 2 to 3 satellites. If 2 satellites are available, here as an example, it can tell the position is somewhere along a circle formed by the intersection of the two spherical ranges. So this is the intersection. So this any point along the circular intersection can tell about the possible locations. So if we are using three satellites, that can narrow down to location on a single point on the Earth's surface rather than with having a possible location. So if we are using three satellites, three or more satellites, the intersection gives a point on the surface of the Earth, and it can pinpoint exact location with remarkable accuracy, and that accuracy may be within a few meters. So this is the way how, by using the concept of trilateration, any point on the earth can be can be measured or estimated by the intersection of three spherical. So more the satellite, the accuracy will be enhanced, augmented. So that is our main idea. Now, when we are talking about GPS system, signal, satellite, the main thing comes about the error sources, which are mainly satellite dependent, that is observation dependent, and the station dependence. For observation dependent, ionospheric delay and the tropospheric delay that contribute much to the GPS error sources. And there is a receiver clock, satellite clock. So there are many factors that I am just enumerating. There are environmental factors, that is there will be some tall buildings, trees which can block or reflect the satellite signals, and it can reduce accuracy. So there may be distortion in the ionosphere and the troposphere which can delay the satellite signals and introduce the positioning error. Also the relative position of the satellites that affects vastly about the quality. So there is also a satellite and receiver clock. The clocks in the satellite are very accurate and maybe up to 3 nanosecond, but there must be a drift in the error that can cause the error in the accuracy. The clock is monitored using that control system, the satellite clock. So the spacing and the position of the satellite in the sky also can augment the ranging error or can reduce. Just like this, there are two satellites that are well spaced, so there is signals, so it can there is an interception of the satellite there can with introducing the low uncertain position. So the satellite, the spacings of the satellite in this way that can augment the ranging error that are called poorly spaced satellite, and there will be a high uncertainty in the position. That uncertainty area is made as a bigger compared to that small uncertainty. So, and there may be some satellites that can include lat, long, height, and time. There are four satellites that can measure this, estimates that four parameters in a very well. So when we are understanding the GPS multipath error, already have talked about the thing of reflection. So GPS signal or the satellite signals can bounce off the surrounding object. It can create the multiple path, so it will take more time to reach the receiver. So inaccuracy will happen. So there will be multiple paths which can interfere with the direct line of sight signal. So suppose there is a lake body is there, so it can, from the satellite the signal is not directly reaching the receiver. It first reaches that point in the lake, and then it has been received by the GPS receiver. So that also can lead to the wrong information and degrade the positioning and the timing accuracy that provided by the GPS systems. There will be some, so to mitigate that we need to adopt some method. So there must be some specialized antenna design that are less sensitive to the multipath signals, which can reduce the impact of reflection. The advanced algorithm can be and remove the multipath components. If we can carefully select the positioning of the GPS receiver, that can minimize the effect by nearby reflective surfaces that has been mentioned in the previous slide, that's lake body. So we have to keep the receiver taking view of consideration the nearby location of the the reflecting surface. So these points have to be kept in. So GPS are mostly used in scientific research, the exploration, survey, and the mapping. So it has revolutionized in a big way. Today, the GPS receivers precisely measure land boundaries, elevation, geographical features. It provides foundation for creating digital maps, the urban planning, the construction, the natural resource management. It can enable the high accurate position and tracking for scientific research fields in geology, geophysics, and GSI is vastly using this the service of GPS for carrying out the National Geophysical Program mapping and all the geophysical problem, geological aspects with the help of GPS. In oceanography, I mean in the field of marine geoscience, the GPS equipped tail buoys, vessels, and already my previous lecture of seismic can be viewed to see that the GPS are there in the tail buoy for marine geoscience. That is GSI, NIO vessels are making use of it, leveraging the use of GPS, and that measure the seafloor topography to understand about the ocean. And for explorer and adventures, it can provide critical navigation, the location, the safety capability in remote and uncharted regions. So we can see there is a vast field of science where the GPS can be leveraged. So the challenges has already been summarized now, told. Now to summarize, we can tell there is a so from satellite the signal is just penetrated by ionosphere. There will be ionospheric delay, and then it receives the GPS receiver nearby to the reflecting surface, which can introduce greater error, and that is called atmospheric distortions in the fluctuation of the ionospheric and troposphere. And there are tall buildings, dense and urban environment that can introduce multipath effects. That there's elevation problem can introduce the multipath effects. There will be, suppose there's a low elevation satellite, there's a high elevation satellite. From the two satellites, there will be in between the signal is coming within an ionosphere, so there will be path error will be introduced in that, which can introduce error in the positioning measurement of that point from the satellites near to the reflect surface. So these points are very much, this have to be mitigated by addressing the problem. So what is the future of GPS? So new generation GPS are having the facility of improved accuracy, signal strength, and coverages. It can integrate AI with the AI ML and allows the GPS to provide smarter waste navigation systems. So augment AR enabled GPS can also provide the improved navigation and gaming application. And recently the high accurate GPS and combined with sensors and artificial intelligence can enable the development of fully autonomous cars, trucks, drones that can I mean that can tell for support for a modernist systems, and it is the future of GPS and with the combined with the emerging technologies. So the limitations are already been summarized, like the accuracy limitation, the susceptibility to the interference effect. Now there will be over reliance on the satellite, which can be vulnerable to interruption from technical issues. And there will also be additional to the privacy concerns, and which can enable tracking and monitoring of the individual without their consent. So these are, if there is a, there are also some limitation and the challenges of that modern GPS technology. This is my part 2 lecture. I'll be quickly delivering the part 3 of the GPS lecture, which will be very beneficial for you, I think, for the upcoming exam patterns. So follow my channel, share it, like it, follow it, and turn on the bell notification icon. And if you are having any problem, please let me know. This is my channel of physics and geophysics learning. Thank you.